recording now. Okay, so I start sharing screen. And do let me know if something is not working for you. Okay. Right, so my name is Hitoshi Murayama. So this is the Physics 151 Quantum Field Theory Primer. So this is the first lecture. And as I said, the lectures will be recorded, get posted on YouTube later. But anyway, let me get started. So this is how I look like. I'm not the guy on the left for obvious reasons. I'm the guy on the right. This is actually a very fun moment for me. So this is actually not the Photoshop or anything. So I was actually invited to be on a TV show in Japan where I was asked to explain this beautiful picture of the black hole I'm sure you have seen 2 years ago. And so in that show, they actually came up with an actor, just a real man, who has the same build as Albert Einstein. And they put this kind of makeup people do on a Star Wars movie and stuff to make him really look like an Einstein. And so he was one of the participants of the show. So after the show, I was so happy to see Mr. Einstein in person. So we're shaking hands. This is a picture. So anyway, so this is the very fun moment for me. So anyway, so the guy on the right is your instructor for this course. A little bit about myself. So I was born in Japan and Tokyo. And part of my childhood, I grew up in Germany. So back then I could speak German. I pretty much forgot it because, I was not using German for a long time. And I can still curse, but that's about as much I can do in German. And I'm a theoretical particle physicist, so that's my specialty. And I use quantum field theory a lot in my own research. And I also worked on a rather wide range of areas: cosmology, astrophysics, condensed matter physics, and so on and so forth. And again, in all of these cases, I use quantum field theory as my tool. So quantum field theory, even though I'm a particle physicist, is not a tool just for particle physics, but also in all kinds of different areas of physics. And so my intention is to basically convey this idea of quantum field theory as a ubiquitous tool in physics, modern physics, and that's the introduction here. I also actually worked on experiment. Even though I'm a theoretical physicist, I actually participated in an underground neutrino experiment called CAMLAND. Berkeley lab was part of this experiment, so I joined in and actually tried to actually set up a collaboration because the CAMLAND experiment happened in Japan. I happened to know people there, and I was working with my colleagues in Berkeley, so I was sort of a middleman to set up the collaboration. But I ended up taking shifts. I participated in construction. I went in the tank, and all you have to do is in a neutrino experiment is to make it incredibly clean. So I spent hours with a cloth and alcohol and just wipe the surface of the stainless steel tank for many, many hours underground. But anyway, so that's what I did. And it was kind of fun. And so we actually managed to really prove that neutrinos are oscillate. And it might come up later in the lecture on that. And I happen to be also a PI of astronomical instrumentation for the Subaru telescope in Mauna Kea in Big Island, Hawaii. So it's a multi-body spectrograph I'm working on right now, again, for studying cosmology and astrophysics in a way that's also related to particle physics. So I do work on a wide variety of things. And as a hobby, I like biking on Berkeley Hills. I also love music. I play double bass. I used to be in an orchestra when I was a student. I occasionally, fool around with playing a little bit of jazz and so on. So anyway, that's who I am. Okay, so about the course. So this is the basic introduction to quantum field theory.
Professor?
And go ahead.
Hi, I'm so sorry to interrupt you real quick.
Oh,
There's a
go ahead, go ahead.
pop-up window
Oh, there's a pop-up window. Let me
that
see. I
seems to be
can.
blocking at least part of the
Oh, it's okay.
screen.
Yeah, I know why that happens. That's the problem with the keynote. I believe this works now. Sorry about that, and thank you for pointing that out. So,
No
I
worries, of
want you
course.
to be very vocal in this class. So, whenever you have questions, don't hesitate to ask. And whenever you have some problems in the Zoom or audio or whatever, then please do point that out. And I stop many times in lectures, pose for questions, and no questions are dumb. I seriously mean that because I do ask a lot of dumb questions when I listen to other people's talks, and that's totally okay. And the physics actually do start with dumb questions because we are a curious bunch. We ask dumb questions that end up really being physics. So I really encourage you to do so. So anyway, about the course. So this is the basic introduction to quantum field theory. And QFT is the foundation of modern physics. And just in case that you're wondering why I'm using this funny animation, I'm using slides for these lectures because my handwriting on iPad don't come out very well. I'm pretty good at writing on a chalkboard, but somehow on an iPad doesn't come out very well. So I'm using these slides. But the problem of using slides is that I tend to go fast. So I'm trying to intentionally slow down by this slow animation to force me to go slowly. But in case you see that I'm going fast, again, please interrupt, stop me, and I can slow down. So again, I'm asking you to be very vocal. This is Berkeley, after all. That's a place for activism. So and that actually shows up in the next couple of bullets, actually. So QFT is the foundation of modern physics, but it's notoriously difficult. And so that's why the department felt that it probably qualifies, it deserves a introductory class on quantum field theory. And this whole course hopefully makes it the whole notion of quantum field theory accessible. And so I try to cover the subjects broadly in many areas of physics: AMO, atomic molecular optical physics, condensed matter physics, astrophysics, particle physics, nuclear physics, and to demonstrate that QFT is indeed a very ubiquitous tool to many areas of physics. So that's what I try to do. And QFT, it turns out that it's a very great tool to incorporate statistical mechanics and relativity as well. So that's the subject we will be touching on. And it turns out that this course was initiated due to strong demands from undergraduate students like you guys. And so there has been, long, keen interest among the undergraduate students to take course on QFT, but department used to offer QFT classes only at the graduate level. And so it turns out that the students who sign up to take those courses find themselves sort of left out, and that was a problem. And so there was a strong demand from you undergraduate students to have a QFT class offered at the undergraduate level. And 2 years ago, the chair back then, Rick Saxton, decided that we should try that. And so we started an experiment. And so this is the third time of doing this experiment, and I am the biggest guinea pig. So as I just said, this is the third time in the department. The first time we did it was in the fall semester in 2019. I also did it again last semester, fall semester 2020. This is the third time, and in the spring semester, and this is a way of gauging whether fall semester or spring semester would work better for this course. So once again, I will be asking you to be vocal at the time of the teaching evaluation, whether you felt like you were well prepared for this course, or you were missing something, and in order to gauge again whether offering in fall or spring makes a better sense. And it's likely to become a permanent offering in the department after this semester. So we will see if that goes. And once again, your input in teaching evaluation will be extremely important for department to decide if this really does become a permanent offering. So I will be asking you once again to be very vocal. And this is meant to bridge the gap between the quantum mechanics you have already taken as a prerequisite, 137A and B, to the graduate level QFT courses. And even though the content is smoothly continuing on from quantum mechanics to QFT, jumping straight ahead to the graduate level QFT courses for undergrad students, as I said already, tends to have a big gap. And so this course is meant to bridge the gap. And also that you may be moving into many different areas of physics. And if you go to grad school, then you may choose one of these areas, not necessarily particle physics I do, but you may be moving into condensed matter, AMO, astrophysics. So this course tries to introduce the use of QFT in all these areas so that when you actually decide to move into one particular area at the graduate level, then you at least have seen something about QFT specifically for your area. So hopefully that would help. So that's at least the idea of what this course is meant to be. So anyways, I stop here just in case you have some questions about what the course is about. Oh, maybe when I stopped once, I did not start recording. Let me stop again.
You're still recording, Professor.
Oh yeah, I'm still recording. Okay, good. I was a little worried about that. Oops, I was not meant to show the music. Start screen. Uh, ah, I know what happens. So if I'm a free screen mode, I don't see that in the choice of the sharing. All these intricacies. Okay, so anyway, so that's what this course is about. Are there any questions about that? Okay, and I specified this textbook with a funny title, Quantum Field Theory for the Gifted Amateur. And I understand that the authors of this textbook are condensed matter experimentalists, but they, of course, do use QFT. And what they felt was the QFT textbooks tend to be written by theorists and what they call practitioners of QFT. And that those textbooks tend to be of a too high bar for many physics students. So they volunteered to write this textbook in the eyes of sort of the consumers instead of the practitioners. And so that's why I felt like this book was the right level for this course. I don't follow it closely. You will find it very quickly, but it does cover the same contents as what this book does. And so I believe that this will be a good reference for you. And so you may have to sort of look around in the contents of the book, just to identify what is being discussed in lectures at that moment. And I encourage you to do so because it does have very useful and also rather pedagogical discussions of every subject I'm going to touch on. But as I said, I don't follow the book closely. So instead, I try to provide lecture notes, which I write. And right now, the lecture notes I've written for the previous semester are already posted on B courses. You're welcome to look at them. And I probably end up rewriting some of that and update them and so on as we go on. But anyway, so you will see what contents get covered in this course by looking at those lecture notes ahead of the time. So I encourage you to do so. So I mentioned this already, the 137 A and B, the undergraduate quantum mechanics are the prerequisites. And I recommend 112, that's the StatMech course, and also 139, that's a course on relativity. And I will do a poll in a moment to see how many of you have actually taken these courses. And I emphasize they are not prerequisites. So if you haven't taken them, that's okay. But I just would like to know how many of you have taken these courses so that I can adjust the level of discussions and contents accordingly. So let me launch the poll. So have you taken Physics 112? That's the course on statistical mechanics. So please fill that out. Great, it's progressing.
If we're taking it now, do we count that as a no or a yes?
I would say no. Okay. So this is the result of the poll. So the majority of you have not taken StatMech yet. So I try to be very pedagogical if I touch on subjects related to StatMech. Okay, very good, thank you. And the next poll is about the relativity. So again, the same set of questions. So have you taken Physics 139 and have you finished taking it? If you're taking now, please answer no. Okay, and basically nobody has taken this course so far. And again, you may be taking it right now, but I do not assume knowledge on relativity when I introduce relativistic quantum field theory later on. So thank you for participating in the poll. This helps me a lot. So just to put QFT in a context, this is something Einstein dreamed of, and that's something we still dream of in physics. So in physics, we deal with many, many different phenomena, right? And we are always looking for some principles behind all these vast phenomena in nature. So we want the principle to be ideally beautiful, simple, which can explain many different things, namely powerful at the same time. And that is what we always talk about as a unified description. So in physics, we face many different phenomena. They look totally different from each other at the first sight, but we are always looking for some underlying simple, beautiful, powerful principle. Einstein himself tried to come up with such a theory, and he tried to unify electromagnetism and also his theory of gravity, namely general relativity, but he actually failed. And in some sense, we are still failing. So just again, put this in context, to what extent we physicists made progress in trying to come up with this simple, beautiful, powerful description of vast phenomena. So here's a little bit of a summary of that. And as you all know, Newton unified an apple and planets, right? He basically figured out that how the planets move is described by the same laws of physics as how an apple falls from a tree. So that's a great unification. So in those days, people didn't imagine that heavenly bodies would obey the same rules as terrestrial bodies because they belong to a different world. But Newton realized that that way moon moves around our planet follows the same law as an apple falling from a tree. And out of that came the Newton's law of mechanics and inverse squared law of gravity. So that's an incredible unification that happened at the point, namely the way bodies move due to the force of gravity is completely the same among everything around us, moons, planets, stars. So that was an incredible step of unification. Another important step of unification you are very familiar with is unification of electricity and magnetism by Maxwell into the theory of electromagnetism. Again, electricity and magnetism might look like totally different phenomena at the first sight, but because of the electromagnetic induction and so on, one induces the other. So we learned that they are actually coming from the same theory of Maxwell's theory of electromagnetism. So this was another important unification which happened in physics. And around the time of Einstein, there was some new phenomena observed in atomic physics, which eventually became quantum mechanics, which was also amazing unification, which actually described all kinds of molecular atomic physics in a single theory. And it's a famous story that Einstein himself didn't believe in quantum mechanics, even though his Nobel Prize was the photoelectric effect, which is actually a very interesting story about that, right? And what Einstein himself did is that he tried to reconcile electromagnetism and mechanics, and that is the theory of special relativity. So electromagnetism follows the Maxwell's equations, and Maxwell's equations was actually not compatible with the Newtonian mechanics. So there were two options, whether to say, okay, maybe there's something wrong with the Maxwell's theory, so that we can stick to Newtonian theory of mechanics, or we expand Newtonian theory of mechanics to make it compatible with electromagnetism. And what Einstein did is choose the latter direction, and he changed Newtonian mechanics into special relativity. So he came up with this radical idea that absolute space and absolute time don't exist. Time is not common to everybody. There's a time dilation effect. Space is not common to everybody. There's a Lorentz contraction effect. And that was a radical idea, obviously, but this is the way he reconciled the mechanics and electromagnetism, and that's a special relativity. But this was not a unification because special relativity does not include electromagnetism. They are compatible, but it doesn't include it. So this was the reconciliation of Newton's mechanics and Maxwell's electromagnetism, but it wasn't a unification. But instead, the unification he did is to make the gravity and special relativity into the single theory of general relativity. So if you're thinking about taking a course on relativity, and this is the area you're going to see, and special relativity is not compatible with gravity at the face value, but once you go to general relativity, it includes both special relativity and gravity in a single theory. So this was a unification. And I'm sure you have heard of this idea that in general relativity, gravity is a curved space-time. Earth moves around the sun, not because the sun is pulling Earth by the universal law of gravity, as Newton pointed out. Because the universal law of gravity is the idea that this is actually a force that happens instantaneously. But in relativity, you can't transmit information faster than the speed of light. So something has to go from the sun to the earth to bend the motion of the earth. So the idea in general relativity is the presence of the sun, which is a massive body and it therefore has a lot of energy according to E equal mc squared. Energy bends space. So earth ends up bending space around it. And earth is moving in that curved space. Earth thinks it's moving straight, but because space is curved, then Earth ends up moving around the sun in a curved orbit. So that's the way the general relativity includes both gravity and special relativity, and that was an important step of unification in physics. But where the quantum field theory comes in is the next step. So now we have this electromagnetism, special relativity, they are compatible to each other. But classical electromagnetism, you have learned in probably physics 7 or 8 or whatever, is not compatible with quantum mechanics because it's a classical theory. We have to put them together. And there were also some discoveries of new phenomena in quantum physics when people studied nuclear physics. So there are three kinds of radioactivities in nuclear physics: alpha decays, which is an emission of alpha particle from nucleus. Alpha particle is the same thing as a nucleus of helium-4 made of 2 neutrons and 2 protons, as you all know. Beta decay of radioactivity is somehow the electron comes out from nucleus, even though electron doesn't exist in nucleus. So how do we understand that is a curious question. Gamma decay is the emission of a photon from the nucleus, and photon is not there in classical electromagnetism. So we have to put them together, and that's the theory called quantum electrodynamics. So this theory is meant to put together special relativity, electromagnetism, quantum mechanics, and phenomena like gamma decay nuclei into a single theory. So quantum electrodynamics is often abbreviated to QED, and so QED is the symbol you use at the end of a proof in mathematics. So, people felt so strongly that this is an incredible achievement in physics. So people decided to adopt this acronym QED as, in some sense, the ultimate theory of electromagnetism. And QED indeed does include special relativity. QED does include electromagnetism. QED does include quantum mechanics and can be applied to nuclear physics like gamma decay. So this was an incredible unification in physics. You don't often hear about it, but this QED is in some sense our goal this semester. So we'll build up quantum field theory, first starting with the non-relativistic systems, because something that you're familiar with, but we build it up. Later on, we include relativity into the framework and include electromagnetism and build QED this semester. And to the extent that you can start using it for some practical calculations using something called Feynman diagrams. And I am going to emphasize later on that QED is indeed an amazingly successful theory. You have learned, I believe, in quantum mechanics class that the G factor of, namely the magnetic moment of the electron, is 2. It turns out that there are corrections to this, so it's not exactly 2, it turns out, and corrections can be computed in perturbation theory using this theory QED. And people have done this calculation incredibly precisely so that there is a prediction, theoretical prediction on the G factor with 12 significant digits. And there is an also experimental measurement of the G factor with 12 significant digits. And all 12 digits agree with each other. So this is probably the most successful theory in physics ever. So the acronym QED actually does make sense in that way. So this is the power of unification. So what Einstein dreamed is to come up with simple, beautiful, and powerful theory, and QED is definitely a prime example of that. So that's an advertisement here that you are going to see QED in the second half of this course. And that is a very, very powerful theory, as I just mentioned, and you get to use it. So that's the sort of the ultimate goal of this semester. And in terms of the progress in physics, the QED was a milestone achievement in physics, but it wasn't enough because there are other phenomena we still need to describe, like nuclear beta decay, which has to do with another kinds of force in nature called weak interaction. And weak interaction turns out to be very similar force as electromagnetism, and which is now unified into the theory of electroweak theory, or sometimes also called the standard model of particle physics. And this electroweak theory, as the name suggests, includes both electrodynamics in QED and weak force of the nuclear beta decay into a single theory. So this is yet another unification we have witnessed in physics, which was achieved only 9 years ago in 2012, when a new particle called the Higgs boson was discovered at the Large Hadron Collider in Europe. And many people in Berkeley actually played a major role in the experiments done at the Large Hadron Collider, and that led to this discovery of the Higgs boson. And with this discovery, now we know that electromagnetism and weak interaction are indeed unified in this electroweak theory. So that's actually fairly new, only 9 years ago. You were already born, I believe. Is any of you younger than 9? Raise your hand. I don't see any hand. Okay, good. So all of you are older than 9, I guess. So does this happen after you were born? So this is a new layer of unification you actually witnessed after you were born. There's yet another force known in nature called the strong force. So nuclear alpha decay turns out to be the first manifestation of this force called strong interaction. And we are yet to see unification of the strong interaction with the other forces. So right now, this is still a hypothesis called grand unified theory. And we don't know if this is true. We don't know any experimental evidence for that yet. But this is another layer of unification people are dreaming about. And people are trying to get some experimental clues on this. And many people in Berkeley are also involved in an experiment called DUNE, which is being constructed. And one purpose of this experiment is look for the experimental evidence of this unification of the strong force and the electroweak forces by observing that the proton in your body is ultimately unstable. And that's one of the predictions of this grand unified theory. I briefly touch on that later on. And if this idea turns out to be true, it still doesn't incorporate gravity. And I'm sure you have heard of the statement that quantum theory of gravity is not there yet. Quantum gravity is another holy grail in physics. And in our department, people like Peter Hojava, Rafael Busso are working in this direction from the theoretical point of view. And the best candidate for the theory of quantum gravity is what is called the string theory. And this is yet another radical idea. When you think of an electron, we think of electron as a point-like particle, but the string theories tell you that it's actually not a point. It's a small rubber band, but it's so small that we think it's a point. By changing a point to a string like a loop, they believe that you can unify gravity, namely general relativity, according to Einstein, with quantum field theory into a single theory of the string theory. So string theory is beyond quantum field theory because of that. Quantum field theory can go all the way up to grand unified theories, but it turns out that string theory still uses the ideas in quantum field theory to describe this theory of quantum gravity. So it turns out that QFT is something you need to know, even when you want to go all the way to string theory. So what I was trying to emphasize here is that physics has been marching through these many different levels of unification in the past. But starting from QED and on, all of these steps are based on QFT. So unless you study QFT, you don't appreciate the level of the powerful theories of QED, standard model, grand unified theory, and also string theory. So the QFT turns out to be really prerequisite to understand all these developments that happened in physics. QED was basically became a theory, complete theory around 1945 or so. Electroweak theory, I told you, became a well-defined theory only 9 years ago. Grand unification is yet to happen. String theory is also yet to be completed, but all of things require QFT. So that's one of the motivations why I hope you would like to study QFT. So let me pause here if there are any questions about this general idea where physics has been going over many centuries. I
This
bet
might
you
be
have heard of
misplaced.
many different ideas. Oh, something wrong? So say that again?
Oh, no, sorry. I was just wondering, does quantum chromodynamics fit in this picture at all, or is that
Yeah,
something separate?
that's a very good question. So the strong force is now described by the quantum chromodynamics, or called QCD. So there wasn't enough space to put that in here. So I should have broken up this arrow into two halves. Strong force led to QCD, which is a quantum field theory description of the strong force. And QCD may be unified with electroweak theory into grand unified theory. So I omitted QCD in this arrow, so I apologize, but the strong force is now also described by yet another QFT called QCD. So that's yet another reason why we need to study quantum field theory, so that we have a well-defined description of the strong force, which ultimately describes alpha decays, nuclear interactions, and so on and so forth. Thank you for that question. Any other questions here? All right. So this is at least one of the motivations why we want to study QFT. So some logistics about this course, homework and exams. So I plan for weekly homework, and we got 14 weeks of lectures, and I counted. So 12 homework seems to be appropriate. Each of them are assigned 100 points. And I'd like to do a poll now about the due dates of homework. So in my past experience, when I actually ask for the preference on what the due dates are preferred by individual students, they tend to fall into two camps, depending on whether you want to use weekends on homework or not. The first camp is you like to keep the weekends free, so you like to rather have homeworks due on Fridays. The second camp wants to spend weekends working on homework and rather prefer due dates on Monday morning. So that's the poll I'd like to do now. So whether you would like to do yes.
Doesn't this depend on when you post the homework too?
So I plan to post homework basically exactly a week before. So if the homeworks are due on Fridays, I plan to post homeworks on Fridays. If I'm a little bit late, maybe during the weekend, but you have 1 week to work on. If the homeworks are due on Mondays, I plan to post homeworks on Mondays. And so that's the idea. So you have 1 full week to work on each of the homeworks.
Okay, thank you.
Okay, so here's the poll. Here we go. So please fill it out. Okay, so there are 29 of you, 28 of you voted. So I guess that's pretty much it. And oh, there, all of you have now voted. So ending poll, share results. So it's overwhelmingly preferring Fridays. So I guess you want to enjoy and the weekends. Of course, this is Bay Area, so plenty of fun things to do. So that's the decision here. So homeworks will be by the end of Fridays. Good. Thank you.
Muted, Professor?
Professor, you muted yourself.
I muted myself. Can you hear me now?
Yeah, we can hear you.
Okay. And once again, I need to change from full screen to screen sharing. I hope they would change the system that I don't have to go through these steps every time. Okay. So we just finished the poll and you guys decided that this is your preference, not Mondays. So that's now decided. And I do encourage you to study in groups because, as I said, the QFT has the reputation of being very difficult. I hope it will be accessible. I try to make it as accessible as possible, as I said, but I really encourage you to study together because there are concepts which may be not quickly sinking into your mind right away. So talking to people would really help you to actually do that. And that's, of course, a little bit complicated in the pandemic, but hopefully you can use Zoom very effectively to make that happen. Do you have Zoom account, every one of you? Just to make sure? Okay, good. And I also plan to have a doodle poll on office hour. Again, I ask for a preference, and I set up the doodle poll already. So my slides are already posted on B courses. You might have seen that under the folder of files and slides. And if you open the PDF file of the slides, you see the link to the doodle poll, which I accidentally clicked just a minute ago. So go to the poll. I try to also put that on the announcements as well to make sure you do have access to the poll. And please fill that out by the end of Thursday so that I can announce the office hour in class on Friday. And I'm planning on take-home midterm, and I assign 200 points for that, date to be decided, and also take-home final, again, 200 points, then date to be decided. So as we go on, then we talk about what dates are actually preferable, again, from your point of view. I already created a Piazza room, so please sign into that, where you can ask questions anonymously. You can, of course, show your names as well, but you can ask questions anonymously in case you feel uncomfortable showing your names and questions. As I emphasized, no questions are stupid, so be courageous, be brave to ask questions. There's no embarrassment you need to worry about. So, but anyway, so this is the Piazza room where you can ask questions anonymously, and we try to respond to questions as quickly as we can and as we go on. And as I'm recording today, all the lectures get recorded. So I give lectures synchronously. So this is in real time, but they get recorded and will be posted on YouTube. And you actually do find lectures on YouTube from the last semester if you're curious to look at them. So if you look up 151 Murayama on YouTube, I'm sure you can find them. So so that's how you get to see the lectures afterwards. So under pandemic, taking notes, watching computer screen, I realize it's a very tricky thing to do. So having access to lectures after the fact, hopefully would help you to catch up with the lectures as we go along. So that's the idea. Any questions about any of these points? So far, so good? Okay. And we have GSI. And his name is Chris Mogney, and here's the email address. And you see his email address also under syllabus on B courses. And he works 10 hours for this class, and other 10 hours he works 137. So he doesn't have full-time availability, unfortunately, but I know he is a very good student. I actually worked with him before on a graduate level QFT course before, so I know he's very competent and capable, and he can answer many questions you might have about QFT. And he's working with Professor Peter Hojava, who is the string theorist in our department. So his area is really about string theory in QFT. So he is a real practitioner of quantum field theory. So you can ask pretty much any questions you like. And I asked him to set up the doodle poll about his office hour again. So you should actually fill that out once he opens the doodle poll. So that's how we like to interact with him. So he will be giving office hour. He will be giving discussion sections, and discussion sections will be taught on Tuesdays 4 to 5, as announced on the department website. If you happen to have a conflict with that hour, then try to make sure that you fill a doodle poll and so that you can actually go to his office hour instead to have the same material covered for you. Okay, so that's the idea about GSI. Any questions about him? Okay, so now we really would like to jump into QFT. So again, I stop many times, I pause many times as we go on, and do ask questions. So when Wick Haxton, as I said, asked me to give a course in QFT as a guinea pig, I sort of understood why that would be a good thing to do, because when I remembered how I felt taking quantum mechanics course when I was an undergraduate student myself, I was extremely frustrated in quantum mechanics course, because all the motivations I was told why I should study quantum mechanics at the beginning of the class had to do with the photon. For example, you get taught that photons coming from atomic excitations or de-excitations come in discrete spectrum in energies. There, you talk about photon carrying energy, which correspond to the energy difference between the initial state of the atom and the final state of the atom, and they come in these discrete bunches of energies. That's the photon. And that's why we need to study quantum mechanics. Photoelectric effect is another reason we need to study quantum mechanics. Even if you shine intense light, if the wavelength is too long, then you can't knock off electron out of the material. And that's because individual photons carry energies whose energy is inversely proportional to the wavelength. And unless the energy of one photon exceeds the binding energy of the electron in the material, you can't knock it out. Again, we're talking about a photon. Compton scattering is another reason why we have to study photon. The classical electromagnetic wave that gets scattered by the electron, that's a Thomson scattering. And in Thomson scattering, classical electromagnetic wave would jiggle electron. And this jiggling motion has an acceleration in it, and therefore accelerating motion of a charged body would emit electromagnetic radiation with the same frequency of the motion of the electron. So incoming electromagnetic wave and outgoing electromagnetic wave have the same frequencies, and that's what you learn in classical electromagnetism. But when you really look at the scattering of gamma ray on the electron, the final state photon has different frequency from the initial state photon because of the energy momentum conservation in relativistic kinematics. So classical electromagnetism doesn't work. That's why you have to go to the quantum theory, you get told. I'm sure you have all heard of this spiel where at the beginning of the quantum mechanics class, why you have to study it. And they all have to do with the photons, but you never see a photon in quantum mechanics. There are other things you have already learned fully about quantization spin from Stern-Gulak experiment, and the spin states are quantized. Therefore, their magnetic moments are also quantized. And when the spins move in a space-dependent magnetic field, their orbits go according to their quantized spin's direction, and that's a Stern-Gerlach experiment. That's something you can fully explain now that you have completed 137A and B. You can also fully explain the electron wave or matter wave in general, like a Davidson and Germer experiment. And so the matter wave is described by the Schrödinger wave function. And you can use Schrödinger wave function to talk about the interference of the waves. And then you can explain this interference in matter wave in double slit experiment, for example. So you can explain the bottom two now, but the top three would require a photon. And at least in quantum mechanics class I took back in undergraduate, I never saw a photon because to describe a photon, you have to quantize electromagnetic field. That's a quantum field theory. And electromagnetism is described using electric field and magnetic field or vector potential as a field. Namely, they are functions of space and time. And what you need to do is quantize this field to describe a photon, and that turns out to be the right idea. To study photon, therefore, you need to know quantum field theory. What you have done in quantum mechanics class is to quantize a particle. And by quantizing a particle, you have found a Schrödinger wave. What we have to do here is sort of the opposite of that. You have electromagnetic wave, and that's the field. And when you quantize a field, you're quantizing a wave. And out of that, you find a particle, namely a photon. So we are going to do the opposite of what we have done in 137. We start with a field, which is a kind of wave. And we quantize a wave and find particle out of the wave. You have quantized a particle and found a wave, matter wave, from the quantization. What we do now is quantize a wave and find a particle out of it. So that's the idea of quantum field theory. And then finally, you get to see a photon so that you can describe the three top bullets of the phenomena so far you have not been able to describe based on quantum mechanics alone. So that's the idea of quantum field theory. Any questions about that?
Professor, could you go over that one more time? Like just the contrast in the difference in, I guess, philosophy in studying regular quantum mechanics versus this one. So in quantum mechanics, we quantize a particle, you say, and study that.
Mm-hmm.
Versus in
Yeah.
quantum field theory, we quantize a field.
Mm-hmm. Right.
Oh.
So quantum field theory, as the name says, is the quantum theory of field. And that's the theory, quantum field theory. Quantum mechanics, again, as the name suggests, is the quantum theory of mechanics of particles. When you have an electron bound inside atoms, you are talking about mechanics of electrons moving in a Coulomb potential. And we know what to do in Newtonian mechanics. Newtonian equations of motion tell you that electron would move in elliptical orbit around the nucleus in the Coulomb potential. That's exactly the same thing as our planet Earth does in the inverse square law of gravity due to the sun. So that's the Newtonian mechanics of particle. And then we go to quantum mechanics, where you go from the Hamiltonian of classical electron, and you quantize it, and now that P and X don't commute anymore. And then you have this funny non-commuting observables called operators. And those operators act on a Hilbert space, described by the Schrödinger wave functions. And that's the quantum theory of mechanics. And that's what you have studied already and understand. So you start with particles, which undergo mechanical description by Newton, and then you switch over to quantized theory, and then you understand the atomic energy levels. That's what you have done. What we do instead is that you start with a theory of waves, like Maxwell's equations, that describe electromagnetic waves, and that's the light. And when you quantize this field theory of electromagnetism, you find quantum theory of fields, and that's the quantum field theory. In that theory, you can describe a photon as a particle. And this is a strange thing about quantum theory. And because we grow up in a world where classical mechanics is a very good approximation, we think particles and waves are totally different things. So our language we developed by interacting with the natural world distinguish the particles from waves in a very, very different ways. So we never think they are the same thing. But what you learned already in quantum mechanics class is that they are actually the same thing. So we always start with the language we have, namely classical mechanics, where you treat objects first as particles, then you quantize mechanical theory of particles and come up with a theory where a particle is at the same time a wave. And that's something we have done in 137A and B. What we do here is the different possible choice. We treat objects around us as waves first, and then that's a classical description. Then we quantize the theory so that you can describe that wave at the same time being a particle. So electromagnetic wave at the same time is a photon. So we go from the opposite direction now in QFT. And that's because of this idea called particle wave duality. So you know electron in maybe freshman physics was a particle following Newtonian equations motion. But after taking 137A and B, now you know it is a wave too. But because we grew up with the language we develop in my daily experience, you want to describe electron as a particle as the beginning. We now know it's not the full theory of electron. And you use this particle description, namely mechanics, as the starting point, and you go through the step called quantization. Then you find the Schrödinger wave equation to describe electron, so it is now a wave too. So the familiar description you have is that you first approximate the quantum systems as the collection of classical particles. That's an approximation. But you use that as the starting point of a discussion. Then you go through this funny process called quantization to come up with a wave description of particles so that it is now both particles and wave. And that's what you have done. But in the case of the photon, that doesn't work. You don't have a classical description of photon as a particle that obeys Newtonian mechanics. Or instead, we have a description of electromagnetic wave using Maxwell's equation. So you have to start as the Maxwell's equation as a first approximation to start your discussion. So you begin with a wave described by the wave equation of the electromagnetic field, and you go through, again, this funny process called quantization, and then you find a particle in there too, so that it is now both wave and particle. And what I'm telling you is that this is because of the limitation of us being mere mortals of human beings. We can't jump into the world to have the right language to describe the quantum systems right off the bat. Our language was developed by our limited experience. We know what to think of a particle. We can picture it like individual dots. They move around following Newtonian's equation of motion. But we know that's not a complete description, so we quantize it to describe the system of electrons, which is both particle and wave. What I'm saying here is that we can also choose a different path. We can describe objects as a wave first, quantize it, and find particle in it. So it is, again, particle and wave at the same time. Either way, we are talking about particle-wave duality. So classical description of particle is not right. Classical description of wave is not right. You have to quantize it either way, and you find a system that has this particle-wave duality in it. So we have to start somewhere because our language and our intuition is limited. And you make a choice whether you want to start with a particle or you want to start with a wave. That's a choice we make in trying to come up with a good description of something at the end is both particle and wave. So that's the change we are going to go through this semester. And everything is both a wave and particle anyway. So that's a choice we can make to choose what is the convenient starting point. And that's what we call the correct classical limit. We know quantum physics is the right physics. Classical physics is incomplete physics. But in the classical limit, we have a good language because we developed it from the interaction with the natural world in our daily experience. So we are limited by that experience to start somewhere using this classical limit. But we can choose classical limit to be either a particle or wave. And that's a choice. And you made a choice last year, probably, in taking 137A and B. And instructor probably didn't tell you that you made a choice. It was implicit, but you made a choice to start with a particle. Then you went through the quantization and you find a wave in it. Now we make a different choice. We start with a wave, go through quantization, and find a particle in it. It turns out that that's the only way you can come up with a theory of photons. But it turns out that it's not limited to photons either. You can also describe electrons or atoms as a wave as the first description, as a classical limit. Sounds totally crazy, but I will tell you later that if you actually look at atomic physics and study Bose-Einstein condensate of cold atoms, they can be described as a classical wave. And I will show you that. So if you happen to grow up in a world at the temperature of nanokelvin, if that's the world you grew up in, then you have seen Bose-Einstein condensates of atoms all around you as you grew up from a baby to a grown-up like you are today. And so describing atoms as a classical wave will be a natural thing for you. But somebody comes in and build a particle accelerator in your world, and using the accelerator, you pump energy into this Bose-Einstein condensate, and you get really surprised that a single atom gets knocked out from the Bose-Einstein condensate. Now you have observed the particle. So what's going on? So if you have grown up in that world, and describing atoms as a wave is a natural choice, but now you are faced with the question, how come this wave produces a particle? That's when you decide to quantize this wave, which obeys the classical field equation, and find a way of describing this particle that came out from this accelerator, knocking out an atom out of the Bose-Einstein condensate. So if you grew up in this hypothetical world at nanokelvin temperature, that would be your natural choice. Unfortunately, we didn't grow up in that nanokelvin temperature, or maybe fortunately, I don't know, depending on the perspective. But given that you grew up in a world where you see atoms as individual objects which look like particles, choosing particle as a first description was the natural choice, and hence you study quantum mechanics. But ultimately, we really need to unify particles and waves, and it turns out, as I said, if you want to describe a photon, you don't have a choice, it turns out. You have to start with a field instead. Hence, you have to study QFT. So choosing wave as the starting point of discussion turns out to be more convenient choice to describe wider variety of objects, not only electron, but also photon and W boson, gluon, Z boson, muon, quarks, and all these particles can be described first as a wave as a starting point. You quantize this wave, which obeys a field equation, and then becomes a quantum field theory where you can see particle degrees of freedom. So we go from the opposite direction from what we have done in 137, and that's the idea of quantum field theory. And of course, right now, I'm sure it sounds very abstract, sounds crazy, sounds bizarre, And that's totally understandable. I felt that way too when I first studied QFT, but that's what we're going to do. You start with describing physical objects as waves first, quantize them, and find particles in them. And that turns out to be much more convenient choice of studying quantum systems, which is more ubiquitous than the quantum mechanics. Any questions about what I just discussed so far? And if you're totally confused, that's totally normal. And I try to deconfuse you as we move on. And so, hopefully I managed to do that. Any questions now? Again, no questions are stupid.
So
Okay.
why
Oh,
are
go ahead.
we taught? Why are we taught the quantum mechanics first compared to what you just discussed? Why? Yeah.
So one of them is historical. Quantum mechanics was discovered first, and quantum field theory was discovered later. Another thing is just the way of pedagogy. So when you learn something totally new and crazy like quantum theory, then you have to learn in steps. And you choose the easier steps. You start making a small step. You learn something really crazy, but you get used to it. You make another small step. But now that you have got familiar with the quantum mechanics, then quantum field theory looks a little less crazy to you. So it turns out from just purely pedagogical point of view, starting with quantum mechanics and then moving to quantum field theory is a easier path, I would say. And of course, excuse me, once human beings become, say, Ubermensch at some point, then maybe we don't have to go through that steps. Then we can just jump into the quantum field theory right away. But because, once again, we get familiar with mechanics in freshman physics first, and then get exposed to quantum physics only afterwards, starting with mechanics is sort of an easier thing to learn, and then moving into quantum field theory later makes it a little bit less difficult, I would say, in studying quantum theory. So it's just a matter of convenience in my mind. Does that answer your question, Jacob?
Yeah.
Okay. Any other questions at this stage? Well, I'm sure you have more questions as we go on. And there are more reasons why you have to study QFT. So it turns out that non-relativistic quantum field theory, which I cover for the first half of this semester, is completely equivalent to multi-particle quantum mechanics, which is kind of reassuring. What I have studied in quantum mechanics was not wrong in that sense. But if they're completely equivalent, why do you have to learn it again by using a different description? But there is actually a matter of convenience in it. When you study multi-particle quantum mechanics, you have a bunch of, let's say, bosons in your system. And let's say you have Avogadro number of them, 6 times 10 to 23. Imagine writing down the Schrodinger wave function for that system. Then for the wave function, you need to have the coordinate for the first atom. You need to have the coordinate for the second atom, dot, and you need to have the coordinate of 6 times 10 to the 23rd atom. So you have a function with 6 times 23 arguments for 3 dimensions. So altogether, that's 18 times 10 to the 23 arguments in a single function. And you can't deal with that. Nobody wants to deal with something like that. So writing down wave function of multi-body system with a macroscopic number of objects is just totally impractical. You have never seen such a wave function. And in quantum mechanics, as I'm sure you have seen, for example, the wave function of 2 electrons in helium atom. Then you have 2 coordinates in it. That sounds manageable. But if you move up to larger number of electrons in the atom, let's say you go up to xenon or something, that's already an argument of, I forgot, how many, what's the atomic number of xenon? Does anybody know? Nobody remembers. Well, we should look it up later. But that already gives you something like maybe 70 arguments in it. So that sounds really pretty impractical. And you also need to impose this condition that the multibody wave function is totally anti-symmetric under the interchange of two electrons because they are fermions, they obey Fermi-Dirac statistics. Or if they are bosons, like in the case of the superfluid helium, you have macroscopic number of helium atoms, and helium is a boson because it has two protons, two neutrons, and two electrons. So altogether, they have even number of fermions. So helium atom as a whole obeys Bose-Einstein statistics. And multibody wave function of helium atoms would be totally symmetric under the interchange of any pair of helium atoms. So your Schrödinger wave function is subject to additional constraint you impose by hand. It's not driven out of any theory, but you just declare the wave function has to be totally antisymmetric or totally symmetric. Maybe you didn't question why because you get taught that way, but if you think about it, where does it come from? It turns out that in QFT, this total symmetrization or anti-symmetrization is an outcome, not something you impose. So once you go to QFT, you don't need to deal with this wave function with 10 to the 23 arguments in it. And if you actually use quantum mechanics as a result, you have to specify your state by putting in these arguments in there for a fixed number of particles. So you can never talk about a process where number of particles changes either. And I will mention that on the next slide. So dealing with the multi-body quantum mechanics has these two limitations. You can deal with wave functions with this huge number of arguments in it when you study macroscopic system in AMO physics or condensed matter physics. That's impossible. So practically, multi-body quantum mechanics is not usable for these systems. So that's one reason why you need to go to QFT. Another reason is that you have to impose this total symmetrization or anti-symmetrization by hand. It's not the outcome of a theory. But if you go to QFT, it turns out to be an outcome of QFT. Symmetrization or anti-symmetrization is a result of your theory, not something you impose on your theory. So quantum mechanics, quantum statistics makes much better sense when you go to QFT. So it turns out that the non-relativistic QFT, as I said, is completely equivalent to multi-particle quantum mechanics, but it's much more versatile formulation of the same physics because you don't need to deal with this macroscopic number of arguments for a function. You don't need to impose symmetrization or anti-symmetrization by hand. They just come out automatically. So it's just a better way of dealing with multi-particle quantum mechanics. That's one motivation for QFT. So this is especially a relevant motivation for those of you who want to go to condensed matter physics or atomic physics, sometimes also astrophysics. Any questions about this? I believe I'm repeating the concepts you have already studied in 137, but I'm pointing out the drawbacks of these concepts when you try to go to condensed matter physics, for example, where you have to deal with this macroscopic number of particles in the system. Okay, any questions? Okay, good. So this is something I said already. There's another reason why you have to go to QFT. As I briefly mentioned already, in quantum mechanics, you deal with these wave functions, and wave function is a function of the coordinates of particles, and function has a fixed number of coordinates. So what that means is that when you want to describe a process, physical process, where number of particles changes, Schrödinger wave function cannot deal with that. So this wave function, which may have this macroscopic number of arguments in it, no matter how large it may be, it has a fixed number of arguments. It's a function in mathematics, and function is a map from some space to another space. And space is fixed. You can change that. So wave function has fixed number of particles in it. Once you fix it, it doesn't change. But what you know is that number of particles can change when you talk about emission of photon from excited state of an atom. How do you describe that using wave function? All of a sudden, number of particles changes from, let's say, a hydrogen atom of 1 electron at an excited state to a state with one electron in a let's say ground state plus additional photon. Then you need to have 2 spatial coordinates for each one of them. And Schrödinger wave function doesn't allow you to deal with that, because then you have to jump the number of coordinates in a function. That's a mathematically nonsensical thing to do. It's just a crazy thing to do. So when you want to describe a process where number of particles can change, then you have to go beyond quantum mechanics. Here, you don't have a choice. So as long as number of particles is fixed, like dealing with a huge number of helium atoms in a Bose-Einstein condensate, you can try to do it in quantum mechanics, which looks impractical, but at least you can try. But when you're dealing with a process where a number of particles changes, the quantum mechanics simply cannot be used because it relies on a wave function, which relies on a fixed number of coordinates or arguments. So that's the limitation of quantum mechanics. But once you go to QFT, you overcome this limitation. So when you talk about photons, which can be emitted or absorbed by an atom, which is the first motivation you're given in quantum mechanics class, you can't do it in quantum mechanics. You have to go to quantum field theory. So that's the message here. In addition, quantum field theory is very flexible. When I mentioned using QFT to describe Bose-Einstein condensate of helium, the helium is a composite object made up of 2 protons, 2 neutrons, and 2 electrons. It's not a fundamental degree of freedom, but you can use QFT to describe this composite object, and it's a very flexible formulation. And when you go to quantum condensed matter class, you often hear about emergent degrees of freedom. So these are degrees of freedom that was not part of your construction, but they sort of emerge once you understand the dynamics of the system. And those things can be described by quantum field theory as well. So it's just a much more flexible formulation. And those emergent phenomena may be, for example, phonon in superfluid. And phonon is sort of the sound wave propagating through the superfluid of a helium. It's an emergent degree of freedom because the fundamental degrees of freedom are protons, neutrons, electrons. But you can describe these degrees of freedom using quantum field theory. And you can also describe the composite states made of 2 electrons called Cooper pairs that appear in a theory of superconductivity. And we will talk about these examples in the first half of this course. So superfluidity and superconductivity turns out to be good examples where quantum field theory can deal with system with macroscopic number of particles. Quantum statistics is automatic. They are built in. And it turns out that they would describe these emergent degree of freedom like phonons in superfluidity or supercurrent in superconductivity. So there is definitely need for using quantum field theory to describe these phenomena. So that's sort of the condensed matter atomic physics motivation for QFT. And in the second half of this course, we move into the relativistic QFT. And the reason is that we know the nature is relativistic. And once you try to combine relativity with quantum mechanics, you can't do this with the standard quantum mechanics formulation at all. Then the quantum field theory is forced on you. Now you don't have a choice. So you can't start with particles. And the reason is that in relativity, I'm sure you have heard of this, even if you have not taken relativity class, X and T, space and time, have to be treated on equal footing in relativity. But if you look at the description in quantum mechanics, you treat X as an operator and T as a parameter. So definitely space and time are not treated on equal footing. So this formulation is not compatible with relativity. So then you might think of two ways to go. One way is QFT, which is to demote X from operator to a parameter. Instead, you talk about a field like electromagnetic field. An electromagnetic field is a function of space and time. And in the electromagnetic field, space is a parameter to describe the position in space for that field. Dynamical degree of freedom is the field, not space. So field is a function of space and time. In it, space, x coordinate, is a parameter. So it's not an operator anymore. So this way, whenever you talk about a field, which is a function of space-time, you are treating space and time on equal footing, which seems compatible with relativity. And so it turns out that relativity and quantum mechanics require quantum field theory. And it turns out that it also leads to, again, unification of relativity in quantum mechanics, which is powerful, so that you find predictions you don't get in non-relativistic quantum mechanics. We talk about spin statistics theorem, which says that the particles of spin integer obey Bose statistics. The particles with spin half odd, like spin 1/2 for the electron, obey Fermi statistics. That is an outcome of relativistic quantum field theory. So you don't even need to wonder anymore. Once you're given a particle in quantum systems, do I need to treat this as a fermion or boson? Because there is no choice anymore. Once you know the spin of the particle, statistics is fixed, which comes to the theorem of the quantum field theory. You also get told to use G factor 2 for the electron in quantum mechanics class, and that's something you need to memorize. But we physicists are proud of the idea that we don't need to memorize anything, right? We can derive everything from fundamental principles. And here we go. In relativistic theory of quantum theory, namely QFT, G factor being 2 is now a prediction of quantum electrodynamics. That's not something you memorize. In addition, you come up with a new prediction that for every particle in nature, they're supposed to be antiparticles. So for an electron, they're supposed to be a positron. For a proton, they're supposed to be antiproton. And we talk about this in the second half of the semester when we try to put together relativity and quantum mechanics into relativistic QFT. And we also talk about yet another theorem called CPT. I'm not going to explain it now, but that's also a very important theorem in relativistic quantum field theory. So you see all these things. So now you go to relativity, then quantum field theory is not something you can avoid anymore. You really do have to face quantum field theory and you have to study it. Okay? So we need quantum field theory whenever you deal with quantum systems that have relativity in it. So for particle physics, nuclear physics, and astrophysics, QFT turns out to be a must. So here's the plan. So we just talked about the question why we need to study QFT. And on Friday, I review quantum mechanics using harmonic oscillator. It's a review. But it turns out that the harmonic oscillator is something we actually end up using a lot in building quantum field theory. So in second week, we start non-relativistic field theory called the Schrödinger field theory. And we try to understand why that theory is completely equivalent to multi-particle quantum mechanics. But once you have the field theory, you can start looking at some immersion phenomena, looking at systems on that is relevant for condensed matter physics, and start applying to Bose-Einstein condensate of cold atoms, and also superfluidity, and also superconductor. and also talk about this general idea called spontaneous symmetry breaking. So that's the first half, all non-relativistic. But second half, we jump into relativity. The first, we would like to quantize the Maxwell field, and that's where you see photon for the first time coming out of theory. And to deal with the photon, we develop a time-dependent perturbation theory. And then you can start talking about emission absorption of photons from atoms, again, for the first time from the first principle. Now that you have photons, you can describe these processes where number of particles actually changes. Then we try to also deal matter particles on equal footing, and first study a theory called Klein-Gordon theory, which is the theory of spin zero particle, and then go to Dirac theory, which is a theory of spin 1/2 particle, and then talk about these important theorems that come out from unification of relativity and the quantum systems, and then talk about Feynman diagrams as practical tools to do computations in relativistic QFT, namely quantum electrodynamics. And if I have any time left, I try to cover some material which may be more topical from, let's say, some recent Nobel Prize or something. So that's the plan of the course this semester. Okay, so let me stop here. This is the end of class today. Are there any questions? Oh, there is a question whether we have discussion section this week, and because discussion sections will be on Tuesdays, we don't have it anymore this week, so it will start next Tuesday. Okay. Any other questions? Okay, so far I'm sure everything sounded crazy and bizarre, but I hope you will get used to it as we move on. And I stopped sharing the screen, I stopped recording, and once the recording is over, then I converted and posted on YouTube, and I put the link to the video on the syllabus page on B courses that you can check it out later on. So that's the idea how I'd like to organize this course. Any further questions? Everything good?
I have a quick
Go ahead.
question. On the, at least on my schedule and on the course catalog, it says discussions are on Thursday from 11 to 12.
Oh, is that right? Maybe I just wrote it wrong because of what I remember from last semester. So let me check once again with Chris and confirm that the Tuesday 11 to 12 you said is the right time slot?
Thursday it says.
Thursday, okay. Tuesday 11 to 12.
Yeah.
Okay. Let me check with him. I'm sorry that
Okay.
I was mistaken, and they announce it again on B courses and also by email to you. Sorry about the mix-up. Thank you for
No
pointing
worries
that
at
out.
all. Thanks. Yeah, no worries.
Any other questions? Everything good? Okay. Great.
Given the poll that we've had recently, so the first homework is going to be released this week Friday or next week Friday?
Yes. Yeah, I'm not going to post homework due this Friday. That will be too short a notice.
Oh, yeah.
Thanks for asking the question. Any other questions? Everything okay? Good. So I see you on Friday.
Thank you so
Stay
much,
safe.
Professor.
Bye.
Thank you.
Are you struggling, Kimberly? Okay, bye-bye.
I did have one question.
Go ahead.
So I'm thinking about auditing this class instead of actually taking it.
I see.
Because I haven't taken 137B yet. I am enrolled in 137B this semester. Yeah.
When's the deadline for you to make the decision? When is the deadline for you to make the decision? Auditing.
I need to check on that whenever the drop date is. But I would definitely like to try to, like attempt the first homework at least, see how that's going. I know like perturbation theory, that's not going to come up in our course for 137B for at least a few weeks.
I see.
I know a couple people in the class already, and they seem to be like, oh, like just take it anyway, it'll be fine, we'll get through this together.
Okay,
but
so we'll see. So as I said, the time-dependent perturbation theory comes up only in the second half of the course. So you may have done it in 137B by then. Then it might not be that big of a problem.
Okay. So yeah, I might try it out. If it's anything like last semester, the drop date was toward the end of the semester, so that wasn't
Oh, right.
as
What's it?
detrimental. Yeah.
Okay, okay.
So if they're like that this semester, then I can always just try to stick it out duration of class. But the other question was, if I did choose to just audit, I think there's like an official way of going about that. Like I think you have to like pay a small fee or something, and then you just kind of.
But you're enrolled as a student, right? Full-time student.
I am enrolled currently, yeah. But if I were to
don't
drop
think
it,
so.
yeah.
I'm afraid I don't really know that. So
Hey,
ask
that's okay.
Heather.
And
Yeah, ask
contact
Heather.
admissions or something. All right. All right. Thank you. It seems like
And
a
let me
really
know once you find out.
yeah, definitely. It looks like a lot of fun though. So I'm looking forward to at least tagging along for a while.
Okay.
All right. Take care.
All right. Bye.